We had some birthday parties. Molly Hibbard turned 90 years old, 90 degrees. And so they having gastronomical delights down there. And I told them to come up here and have some astronomical delights. So people should be kind of filing in. Um, this is the last Science Sunday of this year. We've been doing this for 12 years, going into our 13th year. So welcome all your participation and cooperation. If you have topics you'd like to talk about, I'm looking out at some people in the group here that have given talks before. You're more than welcome. We'd love to have your ideas for what you'd like to talk about or like to hear about. And so that's you can get a hold of me. I'm at 19 Mike 55 at comcast.net, or you can talk to me during or after the proceedings today. Um, in January, the first Science Sunday is going to be on January 7th, Sunday, first Sunday in January. There's only one service that day, 10 o'clock. And so that'll be over at 11. So Science Sunday in January will be at 11:15. The first one in January will be at 11:15. I want to talk about um, fossil genes, about a little bit about how you gain knowledge, what goes on with that, and immortal genes, and some level of the discussion of biology and how actually the cells and chromosomes and amino acids all work together. I hope to give a bit of a introduction or kind of a first course in that kind of talk, and talk about what it means to have genes in our bodies and how they relate to everything else in the world, all other living things in the world. So hope you're there. Remember, January 7th will be at 11:15, and then the next one uh, will be in regular time after that. All right. Uh, Scott has kind of a tradition, a few different traditions during the year, and this one he loves to talk about in the holiday season about cosmic ornaments. And we sure get some great. I think they sent up at your request the Webb telescope
Oh yeah, absolutely.
to help make this a
Yeah,
little bit more gaudy than the last ones have been.
right.
And speaking of gaudy, here's Scott in his sweater.
One of these Decembers, when I talk about cosmic ornaments, I should acquire.
Make sure they can.
Yeah, everybody can hear me, right? I mean, I have a loud, very loud. But one of these years, I want to get an ugly holiday sweater that has galaxies and stars on it. But it's hard. I've got like 3 of these with dinosaurs. It's hard to get away from what you love. Um, hard to get away from a dinosaur too, I guess. So welcome to Science Sunday. As Mike alluded to, this has become a kind of a tradition, cosmic ornaments. There's a lot of, if you get a job as a professional astronomer, a lot of what you do, so I hear, I'm not one, by the way, a lot of what you do is data analysis. You analyze mostly, although this is changing, um, mostly you analyze light. Light can behave in all kinds of strange ways. It can be polarized. The electromagnetic wave can wave in a particular direction. It can be circularly polarized. You can look at the intensity of the light. You can look at the colors of the light. Last time when I talked about pioneering women astronomers, I discussed some of the ways we can decode the science of the stars just by looking at the light that we get from them. And as you probably know, and Dave and I, my husband Dave back there at the AB station, and I recently watched that Netflix short series about World War II and a blind girl called All the Light You Cannot See. And I thought that was a beautiful sentiment, that there's far more light available in the universe, even here on our planet. There's far more light available than the light that we can apprehend with our eyes. And the same is true out in space. There are many frequencies of light that we literally cannot see. And there's some frequencies of light that we cannot see even with our telescopes here on Earth, because different frequencies are blocked by the atmosphere or water in the atmosphere. So humanity has spent a huge amount of money and time and effort and ingenuity to put telescopes up in space. And for the past several years, we've been getting delightful images from space. You're familiar with the Hubble Space Telescope. That's been up there for something like 30 years now, returning beautiful images. But this year, I get to highlight some of the images we're getting from a couple of new telescopes, although we'll have a couple of Hubble pictures in there as well because they continue to be spectacular. All right. All right. I'm not behind the podium because I was told that I pound the podium too much when I talk. Science is very serious. You want to know how things work, you have to study science. All right. So there we go. So I wanted to start off, or actually end. What did I do with my Cepheid variable? I brought it in. Oh, there it is. But I have to retrieve a star. Hang on just a second. So last time when I was talking about women astronomers, I got a question about how do Cepheid variables work. And for those of you who are here or saw the recording online, a Cepheid variable is a star that pulses, kind of like these that are shown on the slide. And interestingly enough, there seems to be throughout the entire universe a constant law of nature that, that we have discovered. So we've made a scientific law, which is our model of a natural law of nature. And we've discovered that Cepheid variables, they have a period. You'll notice that one of these stars is pulsing more quickly than the other. Well, it turns out that the rate of pulsation of these Cepheid variables is directly, calculably, measurably related to their intensity or brightness. So the brighter the star, the faster it pulsates. And this is just a linear relationship, and it holds throughout the cosmos. And this is one of the ways that scientists first determined that things like other galaxies exist very far away, is because if you know the pulsation period of these, that linear relationship to determine what brightness they have inherently, right? Because their pulsation is related to their brightness, just like if you take a light bulb and you put it further away, it looks dimmer. Well, the same thing happens with stars. So you can determine how far away a Cepheid variable is just by looking at its rate of pulsation, which is pretty straightforward to measure, right? So astronomers spend a lot of their time looking at these kind of numeric surveys of the sky that indicate the colors and pulsation periods and whatnot of the stars. And the particular kind of stars, these Cepheid variable stars, are an important rung on what's known as the cosmic distance ladder, which I'll talk more about in a few minutes. Dave, am I moving around too much for your camera, or is this okay? I'm fine. Good. All right. So anyway, at the end of the last Science Sunday that I gave, I got a question about how do Cepheid variables work, and I made some mealy-mouthed answer. Oh, it's all thermodynamics. Well, yeah, but how do they work? So I did a little more research into this, and in the outer layers of a Cepheid variable, there's helium that builds up in the later stages of the life of stars within a particular mass range. And helium, as you all remember from high school science, helium has 2 protons, 2 neutrons in the nucleus, and 2 electrons. It's the second simplest element after hydrogen, which has only 1 proton and 1 electron. Well, one of the things that happens in these Cepheid stars that's actually responsible for the pulsation is that the helium in the outer layers of the star absorbs so much energy that their electrons fly off, becomes what's called doubly ionized. And doubly ionized helium, or 2 protons and 2 neutrons with no electrons around them, is really good at absorbing light. So the outer layers of the star become more opaque and they absorb more light. Well, that means they absorb more heat. And as a ball of gas or nearly anything absorbs heat, even a steel bridge or whatever, it'll expand, right? So the star expands because the helium is doubly ionized and absorbing some light. So the outer layers of the star expand, and that causes it to look dimmer, right? Because you've got the same amount of energy, but a larger surface area that energy has to leave from. So the star looks dimmer and larger because of the doubly ionized helium, but it's now puffed out a bit, and so it starts cooling off. So it cools off, the electrons find their helium atoms. Hey, I know you. You're not the one I started with, but hey, you're as good as the next guy, right? And the electrons come back, and gravity pulls the layers back in again, and it compresses again. And the star seems to get brighter. And so this pulsation is driven by this cyclic um, heating and ionization of this layer of helium in the outer parts of the star. And this works all over the universe. It's one of the great things about the laws of nature. They don't just work in your house. They work everywhere in the cosmos, from the beginning of the Big Bang till the unforeseeable future. The laws of nature don't change. And one of the tasks humanity has set itself, especially in the past 200 or 300 years, is to discover these laws and to try and write them down in a way that other human beings can understand. So I like to distinguish between a scientific law and a law of nature. A law of nature is just the way it is. Scientific law is our best approximation for a law of nature. And I talk about that quite a bit in my first book, which is available on Amazon. And I talked about my books a while back. But anyway, I brought with me a Cepheid variable star that Joanne and I made the other day. This is my Cepheid variable star. And you may not recognize it as a star. So I brought a little visual aid. Oh, here we go. Now it is a star. All right? Clearly a star. Any questions? All right. No, I don't think so, but thanks, Mike. I need to hook up my battery, though. Stars need an energy source. Yeah, Cepheids have an energy source. It's nuclear fusion. Unfortunately, I couldn't fit a fusion reactor into the palm of my hand. Maybe give it 100 years, right? Okay, and then I have to turn this on. I don't know. This is a mechanical kind of project, and I'm not good at that kind of, dealing with real things. All right, so the energy of the star, the light coming out of the star is like radiation pressure. In fact, that's what it's called. It's called radiation pressure. And that's what keeps any star that's actively fusing fuel in its core, that's what keeps a star from collapsing, is the radiation pressure. And then it also builds up different convective currents, like a boiling kettle of water or whatnot. And convective currents transport energy, and then the photons transport energy out of the star eventually. So anyway, I've got this Cepheid variable, and I'm going to turn on the core of the star here, and we're going to have an energy source, and we're going to see this outer layer. And then you'll notice that when the energy coming out of the star, the core of the star is fairly modest, the outer layer just sort of wiggles a little bit. But if I really turn up the energy coming from the core of the star, the pulsation rate increases, right? You see that? So I wanted to originally do this with a steam kettle, and then I thought, well, I'm a klutz, and I'll probably end up scalding myself. So Joanne and I built this out of some spare parts I had in my house. So this is, you see the pulsation there, right? It's just proportional to the speed of the air going around it. So as I turn it down a little bit, the pulsation period changes. So it's what's called in physics, it's called a restoring force, right? You've got constant force on something. If that something has the ability to move, like you've seen steam engines with a little flap on the end of the thing, and it's going down and it's right, and that's kind of a restoring force, and it automatically sets up a periodic motion. And periodic motions in mathematics and science are described by sine waves and cosine waves, which is why you all bothered to study trigonometry in high school, because you needed to understand that demo. So makes sense, right? All right. So that's kind of how a Cepheid variable works. All right, now let's get into today's topic. I mean, Cepheid variables are cool and or hot, depending, right? And but I want to talk about some other beautiful things in the cosmos. So here we go for this year. First thing, a messenger from outer space came barreling through our atmosphere, I think in 2021, and the data was finally decoded and analyzed. Again, you're an astronomer, you spend most of your time in a dark room looking at a computer screen. Well, I guess it could be a bright room for that matter. Telescopes are all controlled by robots, and so you don't have to physically manipulate a telescope. Anyway, there's a series of particle detectors out in the desert of Utah. And whenever a high energy particle from space, you've heard of cosmic rays, right? Whenever a cosmic ray comes in and hits the Earth's atmosphere, if the cosmic ray is energetic enough, it will cause a cascade or a shower, a particle shower. So the high energy, in fact, the highest energy particles typically don't make it to the ground. They're not detected by these arrays in Utah and Antarctica and other places, right? But the shower is detected. And if you add up all the energy from all the particles that are detected, you can extrapolate backwards and say, well, how heavy was the atmosphere hit? How hard was it hit? How much energy was imparted into the upper reaches of the atmosphere to cause this kind of cascade? And so the one that's modeled, the question is, for those who need a microphone online to hear, the question is, are these photons? Typically not. Typically um, they're atomic nuclei. They could be hydrogen nuclei. So what's the nucleus of hydrogen? One proton, right? So a lot of times you model these things by saying what's the energy that one proton has to have in order to account for the cosmic ray shower. But there's a lot of these cosmic rays are iron nuclei. So iron is the poison pill of stars. I've talked about that before, but I'm not going to get into it today. But there's a lot of iron flying around space that has been ejected largely because of supernovas. So it could be an iron nuclei, it could be a helium nuclei, it could be a, but it had a huge amount of energy. Whatever it was, it had a huge amount of energy. How huge? It had 240 exa-electron volts. Wow! How many of you are astonished by that? Yeah, all right. Exa, giga, giga, uh, tera, peta, and then exa, right? Oh, I'm sorry. Now you, okay, all right. So I've had you doing trigonometry. We'll do a little bit of arithmetic. 240 times 10 to the 18th, that's 18, one with 18 zeros. I don't have time to read that out. I got a lot of slides to get through. The Large Hadron Collider in Geneva, most powerful particle accelerator ever built by the hands of humanity, is 1.36 times 10 to the 13th electron volts, whereas this cosmic ray was 10 to the 19th. So 18, 17, 16, 15, 14, 13. That's 6 zeros. That's a million times, right? So it was a million times more energetic than the particles we can make with the Large Hadron Collider, which is one of the reasons particle physicists and astronomers and cosmologists and science geeks love cosmic rays, is because they can produce debris showers that even our biggest particle collider can't do. A million times bigger. Think of the budget that would require. We'd have to get rid of all the wars. So this was actually the second most energetic particle ever recorded. The most energetic one was in 1991 called the Oh My God particle. because physicists can get a bit overwrought, and astronomers, they get excited by things, and it was the, oh my God, particle. What was that thing? And that was 320 exa-electron volts. So not an order of magnitude different, but about, what, 75% more, something like that. All right. So there's some mysteries around these things. I mean, okay, great. It's a big energetic particle. Wow. How many of those do we get? Yeah, we get quite a few that are a little bit under that, right? But why are these so amazing other than their particle showers? Because they shouldn't exist. Space is full of microwave radiation, called the cosmic microwave background. And one of the things that happens when you move quickly toward a source of light is you get a Doppler shift, right? Just like a train. I can do a great Doppler shift. Let me do it for you. It goes, right? You know, right when it goes by you, right? But the, right, that part is when it's coming toward you, or you could be coming toward it, right? The frequency goes up, the energy goes up. So you get your cosmic microwave background radiation, and you're zooming through it at 240 electron volts. The cosmic microwave background looks and acts upon you as if, in fact, they are gamma rays. This is a consequence of relativity theory. So you're plowing through an ocean of gamma rays as a single particle. What should you do? You should split apart and slow down, right? Where do these suckers come from? How far away are they made? How do they survive their travel in outer space, bathed by blue-shifted cosmic microwaves? I don't know. Figure it out. Get a Nobel Prize. That's why scientists are fascinated by these things. Oh, by the way, speaking of relativity, if you're 1.5 billion light years away, so you're a significant distance toward the edge of the observable universe, you know, more than 10%. If you start off your trip 1.5 billion light years away and you're headed smack for Earth, it'll take you a couple of days to get here. This is called relativistic time dilation. So in the reference frame associated with these moving particles, they could have started out a billion light years away. A light year is 6 trillion miles. So a billion times 6 trillion. I'll leave that as an exercise for you at home, right? That many miles away, and it travels all that distance in a matter of days. Well, how can that be? Nothing travels faster than light. You already told me that it's a billion light years away. Well, it's because clocks behave in a funky kind of way due to relativistic effects, which I won't go into. This is not a relativity lecture. You'll have to come back to that. All right. So we've got this telescope out there. You may have heard of it, called the James Webb Space Telescope. And it is specially constructed and maintained in such a way that it is hypersensitive to infrared light. This is the kind of light that snakes could see, can see, many snakes. So if you were a snake with a telescope, you could see a different universe. But we are stuck with our visible light eyes, but astronomers discovered that there's a lot to know. There's a lot to learn by looking at infrared light. So they put up a couple of special telescopes just to look at infrared. This was the latest one. All right, so here's a pedestrian view of Uranus. Uranus, in case there's any question. This is a close-up view of Uranus. This was taken by Voyager 2 in 1986. It's kind of a snowball planet, right? It's got a lot of frozen ammonia and some frozen water crystals and whatnot. I mean, it's cool. It's another planet. That's cool. Here's the picture of that thing. Oh, a couple facts. It's got an 84-year orbit around the sun, and it rotates on its side. So something, the theory is something walloped it a long time ago and caused it to flip over on its side. So it's been rotating like this forever. Well, you know, long time. Forever is not something physicists like to talk about. But this is James Webb Space Telescope picture of that same critter, you'll notice that it might remind you of Saturn because it has rings. Well, Uranus has rings, but it's further away. It's cooler out there. The light that we can obtain from the rings is very dim, but it's pretty bright in the infrared because the rings get heated up, right? Hot things cause infrared. So this is a picture, and you can actually see a couple little clouds. That's a cloud. That's a cloud. These are not optical artifacts. These are really out there on Uranus. Uranus. And this is a denser kind of polar ice cap, or a denser area of the atmosphere near the pole. So these are not visual artifacts from the camera. This is the way the planet looks to Uranus or to Webb. So you can extract more science about the atmospheric convective currents and how long it takes for clouds to come and go and what the seasons may be on this planet, etc., by looking at a different kind of light, all the light we cannot see. Yeah, we have a question. Mike, do you have the mic? Well, the problem is people online can't hear you, just can't hear you without a microphone. So we'll get a microphone here.
Test. Okay.
My question is concerns the visual effect there. Are we invited to think of that as a shell as opposed to a ring? Is that going to be an atmospheric shell that the Webb telescope can see through to a much denser planetary core?
That's a great question. Thank you for asking it. The answer is no. All right, next slide. We've got, these are rings. So you've got, anytime you have a swarm of particles, think of buzzing bees. Anytime you have a swarm of particles moving with random trajectories, they'll tend to collide with each other. A collision in astrophysics means you get close enough to feel its gravity, right? Things don't very often actually hit one another. But in a ring system, you may actually have real collisions. And so the particles get broken apart and turned into dust and snowballs or whatever. But if you do a simulation on a supercomputer, you'll find that over time, the various random linear momenta of these particles in this swarm, because of the collisions, that linear momentum is translated almost universally to angular momentum, and it all forms a disk. So disks are common astrophysical objects. Protostars, protoplanets, these are the baby stages of accretion when material is coming in to form stars and planets. Those baby stages of astronomical body formation always involve the creation of some kind of disk. So these are in a disk. So these really are ring or hoops around the planet. They're not shells.
So does it work out that at some point the pole of Uranus is pointing right at Webb so that we can see this?
Yeah.
Okay, that's interesting.
All right. Now I want to talk a little bit about the most distant galaxies. This is not a picture of one of those. This is the closest large galaxy. Wonderful target for those of you who have telescopes. Disappointing. Anyway, you can see these with binoculars too, right? This is the Andromeda Galaxy. It's about 2.1 million light years away and about 100,000 light years across. And it's got Cepheid variables, so this is one of the first things that astronomers were able to determine the distance to, right? And there was a big argument for more than a century about whether this was a cloud of stuff in our own galaxy or whether it was a whole other galaxy. I mean, why would God create more than one? One seems to be plenty for all we need, right? So there was a little pushback from people who had a theological disposition, and then astronomers said, no, it's a lot bigger than you think. And this was one of the first large galaxies discovered outside of the Milky Way, and it looks similar to the Milky Way. But anyway, this is a close-up, beautiful view of a galaxy. And this is the same galaxy viewed in infrared. So again, all the light you cannot see gives you more information about interesting happenings inside a galaxy. The thing that's emphasized there, this little dot, this is a brightness spectrum over time for this little dot. Turns out that's a neutron star. A neutron star is about the same size as Manhattan. And it's got the mass of more than our sun compacted into a stellar remnant about the size of Manhattan. So we can see something about the size of Manhattan with this telescope, but kind of, right? This is just the light coming off of that really bright core. It's the core of a dead star, but it's still millions of degrees, so it emits a lot of light. Anyway, they found this neutron star core by looking at the infrared image of the Andromeda Galaxy. So you can find all kinds of things. You can find, swirling lanes of hotter gas within the Andromeda Galaxy that seem to comport well with the image we have in visible light of the Veris spiral arms. So a lot of science can be extracted. Yeah.
In that heated area, do we see planetary formations?
No, we can't.
Stars?
Yeah, we can't, as far as I know, we can't resolve any planetary formation. We see dust clouds and gas clouds that remind us of things like the Orion Nebula, which I'm going to talk about if I have time today. But you can't see the individual planetary systems forming. All right, so this is a picture. That's why I showed the other picture first, because this one's like, that little guy right there. This is a galaxy, or a proto-galaxy. And this galaxy has been around since the universe was 300 to 400 million years old. This is one of the earliest condensed light-emitting blobs that we could possibly see, right? Because beyond this, you get into a region where the universe is filled with so much ionized gas. Think of the Cepheid variables and the ionized helium that absorbs light, right? The universe was so dense with matter, and all that matter was ionized, and so it was opaque to light. So you try to look much beyond this, and you'll just see darkness, literally darkness. You won't see a glowing sky. You'll see darkness because light couldn't get out of the universe. When you look back in space, you're looking back in time. This was one of the earliest possible things we could see in the universe. And it's something like 13.4 billion light years away. That's a long way. 13.4 billion times 6 trillion. All right? That's how many miles away it is. Easy. And one of the things about the earliest stars of the universe, I gave a whole lecture about this a year or so ago. Most of you weren't around because it was a pandemic, and I was talking to an empty room, and Mike. Thank you for keeping me company. I talked about the search for the oldest stars in the universe. And that's one of the primary missions of the James Webb Space Telescope, is to look for the universe's very first stars. It is widely expected that the very first stars in the universe will be completely different than any other stars we can see nearby. And by nearby, I mean within, like 11 or 12 billion light years. So the first stars in the universe didn't have any heavy elements to work with. Astronomers, they come up with goofy names, and they also come up with some goofy twists on science, like the idea that anything that's not hydrogen and helium is a metal. Carbon is a metal, nitrogen is a metal, sulfur is a metal to an astronomer, all right? You have to be very delicate around them. They get their chemistry confused. All right, so that little red splotch, and by the way, this other thing is a galaxy too. It's just not, it's not as interesting. It's closer, right? But that is one of the oldest things we could possibly see in the universe. And these kinds of very distant galaxies are expected to have a population of ancient stars. And some of the first stars that ever burst forth into the universe are expected to have been hundreds of times more massive than our sun. Many of them are thought to have burned through their fuel in thousands of years, as opposed to billions, and then collapsed directly into black holes. That might have been the seeds for some of the supermassive black holes we see in the centers of galaxies. So there's all kinds of cosmological unsolved questions about where supermassive black holes come from, what the first stars look like, what their chemical composition was, what the first galaxies were like, how big were they, how did they accrete mass, all kinds of stuff that the Webb telescope will help us answer by looking at these little boring red blobs. All right. So what happens to a star at the end of its life? I told you about neutron stars. That's the leftover hot glowing core of a dead star. As a star approaches the end of its life, it tends to puff out its outer layers. It starts burning and synthesizing heavier and heavier elements, and that causes the outer layers of the star to sort of waft off into space because the star that they surround is getting hotter and hotter, and they can reach escape velocity, and you get these beautiful shells of gas around old stars. But eventually they go kablooey. When they go kablooey, it synthesizes a bunch of heavy elements like platinum and gold and whatnot. And if I can make it through today's talk, I'll talk more about gold. Who doesn't like gold ornaments, right? And one of the things that astronomers have tried to figure out is the rate of expansion of the universe. The universe is expanding, as you learned from a Monty Python movie. And strangely enough, the rate of expansion is changing over time. And it's called the Hubble parameter. So that right now there's an expansion rate of our universe in our relatively local reference frame. And that we call that H0. So that's the current value of the Hubble parameter. And sometimes that's called the Hubble constant. But the Hubble constant isn't constant. The universe, the rate of expansion of the universe changes over time, and astronomers are trying to figure out what that rate is. What's the rate of change of the expansion of the universe? And that's the description of the Hubble parameter. And the rate of change, it's like an acceleration, 9.8 meters per second is an acceleration. Even though your speed at any time changes, your acceleration remains constant, right? So the Hubble parameter could be constant, but it changes a little. But when you look at it over vast distances, you can kind of figure out what the average Hubble expansion value is since the beginning of the universe. And you can come up with a number by looking at supernova that I'm likely to get these flipped. So if anybody's trying to answer a coursework from my talk, look this up for yourself. I'm like ChatGPT, I hallucinate. If you look at supernova, which you can measure very far away, that on the cosmic distance ladder, supernova give you another rung to understand how far and how bright things are away in space. If you look at supernova, you get an answer of something like 67 megaparsecs per year, something like that. I'm likely to get these units wrong too. 67 is the number. That's the rate of expansion of the universe. But if you look at the cosmic microwave background, you see all these little wiggles? This is a picture of the infant universe. This was back when it was so hot that remember I talked about that big ball of opaque gas? Well, for a little while before that, even that ball of gas was hot enough to emit light. So we see baby galaxies, and then we see nothing, and then we run smack into the cosmic microwave background. So that is the surface of the universe as it existed about 13.7 billion light years ago.
That's the picture on the right-hand side here, just for clarity.
Yeah, that's the pockmarked one over there. All right, and these little pockmarks are temperature variations in the cosmic microwave background. So the cosmic microwave background is about 4.7 degrees Kelvin, absolute, right? Just a little bit above absolute zero. When the light was first emitted that we see as microwaves, that light was was infrared approaching red. So you could probably see it as a dim red glow if you were right there. Of course, you wouldn't be right there because there was no carbon and oxygen and all that stuff, and no you. So anyway, these are variations from that 4.7 degrees Kelvin. These variations, these little bumps, the red spots are a little warmer, the blue spots are a little colder. These variations are something like a microkelvin, right? 1/100th or 1/1000th of a degree difference. Imagine the technology it takes to measure 1,000th of a degree difference over the entire sky, looking only at the microwave background. Amazing stuff we can do with the light we can't see. Anyway, the scale of these temperature variations, how big those little dots are, tells physicists, astrophysicists, a lot about the distribution of matter versus dark matter in the early universe and the temperature of the early universe. They can also deduce things like which elements should be more or less abundant in the early universe at this stage. And all of those predictions have turned out to be validated by subsequent observations about the element abundances and the scale variation of structures in the universe and whatnot. It all agrees perfectly. Well, one of the things they can do is they can figure out the rate of expansion of the universe, which is related to the cooling effect. Things expand and they cool. They can figure out the rate of expansion of the universe, this Hubble parameter, by looking at the cosmic microwave. And they come up with a number of 73. So why should we have two different rates of expansion for a universe? I've had the constant rate of expansion for about 40 years. I haven't had two. I can't expand at two different rates at the same time. I doubt you can, right? What does it mean for something to have two different rates of expansion? Something has to give. So one of the more recent ideas is that there's this sort of web-like structure to the distribution of galaxies and clusters of galaxies in the universe. And the idea is that we live on the edge of a cosmological void. And if you look at the equations of general relativity, which I'm sure you've all done, and you try to solve them, you find quickly that they're unsolvable. So Einstein came up with this wonderful theory of gravity that has no solution, except in very special cases. Those are called, it's an analytic solution where you can work through the algebra and the matrix algebra and whatnot, and you can come up with a numeric solution, right? That's the way you solve problems, is you start with some equations that describe the state of the thing, and then you end up with some numbers that tell you about the properties of the thing. You can't do that with Einstein's theory of gravity, except in very special cases. Instead, we use computers to simulate it, right? But in any case, there is a special case that has been solved. And that special case is the universe is completely homogeneous and isotropic. So it's made of the same stuff everywhere you go. And the density of that stuff is the same no matter where you go. And as soon as you make those assumptions about the way the universe is, you come up with a solution to Einstein's equations that tell you about the rate of expansion of the universe, and you can get all these nice numeric things out of them. But it may be that that assumption that the universe is isotropic and homogeneous, it may be that that needs to be called into question. It may be that these voids in the cosmic web are so big that we can no longer assume that the universe is isotropic, homogeneous everywhere. And if that's true, it means that you start having the effects of relativity about time dilation and the relative differences between measuring distance scales. Some of those things might become important. So maybe that's part of the solution for why, if you look at the earliest picture we can see of the universe versus the data we get from supernova, which are much more mature stars and are younger than the cosmic microwave background, maybe one of the reasons they're different is because our assumptions about the structure of the universe is different. Wouldn't that be cool to know? So that's part of the reason that this so-called Hubble tension is important to physicists. They have to explain it. They have to. Nature does it. Why does nature work that way? How can we model it? All right. Speaking of disks, This is the famous Herbig-Haro object. There are lots of these up in the sky. For those of you who don't want to go around saying Herbig-Haro, have you seen the latest Herbig-Haro object? You can just say HH. That's the way most astronomers talk about them, the HH object. And this is HH 797. There's many more than 1,000 of these. And what's going on here? Like a cosmic slime or something, right? Well, right here, you see this little gap where the color changes and they seem to kind of come down to a point right here? That is a baby solar system, right? Herbig-Haro objects are associated with newborn solar systems and newborn stars. But right in the center, it is so clogged with gas and dust and other debris from the formation of a star and planets that you can't see it. It's opaque, even to the James Webb Telescope. But you can see really close to it. And so these are jets of ejected matter. So this is common in astronomy. You have many, like quasars and whatnot. You've got many contexts in which you get jets of material coming off of an object. And this is a newborn solar system. And you know, if you looked at this before you had the James Webb Telescope, you'd see a little red smear and a little red and maybe a little white smear here. But the James Webb Telescope allows us to see, you see these like little clumps here, these little like shock fronts right there, right there, right there, right there. If you're an astronomer and you look at those carefully and you do the calculations, what you deduce is that there are actually two baby stars in there. And as they orbit each other, they cause these shock waves in the ejecta. And you can figure that out just by looking at this light. Isn't that astonishing? Speaking of astonishing stars, there's this planet, LHS 3154b. The star would be 3154a. And the planet is a significant fraction of the size of its star. So it's much bigger than Jupiter, and this star is much smaller than the sun, and they're comparable. They're like kind of like the Earth and Moon, right? They're kind of within one order of magnitude or so of each other. Of each other. And current theories of stellar formation and planet formation say, that ain't possible. The universe is like, yeah, watch this, right? Nobody knows how that came to be yet. Give them a few years. Right. What else have we got out there? Okay, so this is the constellation Orion. I told you I'd talk about that. You recognize it? The belt of Orion and the sword of Orion and everybody's favorite, well, among your favorite stars is likely Betelgeuse, right there, big red star. Likely to go boom sometime soon, maybe tomorrow, maybe 10,000 years from now. Anyway, so this is the famous Orion Nebula. Now let's take a look at this where we emphasize the light emitted by hydrogen gas. This is the same area of the sky, zoomed in a little bit, but essentially, you know, this is Betelgeuse up here. Rigel is down here, but we're mostly emphasizing the hydrogen. And this is called the Barnard Loop. It's a giant shell of gas. There's lots of gunk in the constellation Orion. It's one of the richest places to look in the universe if you want to get great pictures and great science. So we can zoom in at on this guy, and that's the Orion Nebula. This is like a cocoon in which baby stars are being born at a furious rate. One of the places in our galaxy, as far as we know, where new stars are just popping into existence over time, you know, over a period of thousands of years, kind of thing. And you know, you see the gas and dust around it, and right here where it's brightest, there's a whole bunch of new, really massive, really hot stars that are kind of lighting up a lot of the material around them. And these are the kinds of pictures you can get. In fact, I've got a picture I took that looks very much like this that I took with a little backyard telescope. And You can do this. Just go buy a telescope. Talk to me first. You don't want to get one like from Costco or whatever. Anyway, you can get pictures like this. And this is the Orion Nebula, and it's gorgeous, right? But the Webb telescope can really zoom in. I mean, this is really zoomed in. You see this dot here and this dot here and this little dot here and this tiny little dot here and this little. Those are Jupiter mass binary objects. If you had this picture to look at close, you would see that each of those dots is actually two dots side by side. You can resolve two dots. And these are Jupiter mass binary objects that are not gravitationally bound to a star. They're just floating around in the Orion Nebula. Oh, there goes a planet. Oh, well, actually, there's two, right? Where do those come from? Why are they loose? Who let them out? These are good questions. Who let the Jupiters out? Okay. So the Webb telescope lets us see all that kind of stuff. You can see shrapnel from a star collision. Did you know that shrapnel is the name of a British Army guy? That was his last name, was Shrapnel. He invented the shrapnel shell. Anyway, in the Orion Nebula, within the past 1,000 years or so, there was two stars that got too close. They probably didn't actually run into each other. It's really hard to get things to actually hit each other in astronomy because it's mostly empty space. Things tend to orbit really close and then fly off. But that's called a collision. And it can really cause a mess. The outer layers of the stars get blown off and whatnot. So this is also in the Orion Nebula. You can't get this with your backyard telescope, but the Webb telescope can. You see it. Amazing stuff. And then there's this thing, the brick. Inside the Orion Nebula, there's this dark cloud, and astronomers knew about it for a while. They expected to look at it with the James Webb Telescope and see heat signatures of baby stars. You get a dense cloud of gas and dust, and within that dense cloud, almost inevitably, you're going to have new stars forming, right? They looked in here, and they didn't see any new stars forming. It's just a big, dense cloud of gas and dust. How did that happen? I don't know. Graduate students are going to get a PhD trying to figure that out. This is a picture from the Webb telescope of a galaxy cluster. I think every dot you see here is a galaxy. This is a galaxy. It's kind of an edge-on spiral. This is a spiral galaxy like the Andromeda galaxy I showed you before. These little red blotches are galaxies that are further away that are being magnified by something called gravitational lensing, which I don't have time to talk about. This is also a gravitationally lensed image of a single galaxy. Thousands of galaxies to study in this one picture, including perhaps some of the oldest galaxies in the universe, these dim little red dots. Why is there so much stuff? Is there a limit to how much stuff there could be in the universe? These are interesting questions. All right, this is a star that's nearing the end of its life. I told you as a star ages, it puffs out its outer layers. This is a bunch of debris from a star that's about 3,000. No, I'm sorry. It can't have a star that big. This is the cloud of gas and dust that's about 3,000 times the mass of the sun. And you've got newly forming stars. You've got dust from stars at the end of their life. It's just a mess. So figuring this out is something that would be fun for astronomers. You talked about shells. This is a shell galaxy. This is Hubble, right? Hubble's still up there. Hubble took this beautiful picture of these shells. This is not an artifact of the resolution of the picture like you see on your TV screen where you get some banding. These are real shells of stars around this galaxy. Almost certainly the result of a collision with other galaxies where stars were agglomerated into this shell-like onion. It's like a cosmic onion. Here's a picture of a galaxy from Earth, and here's the same galaxy from Spitzer. Spitzer was the predecessor to Webb. This is an infrared picture of the same galaxy. You can see the voids here where there's not hot gas and dust. You can see the hot nucleus of the galaxy here. And this is the Webb view of that same stuff. Lots of juicy science can be squeezed out of pictures like this. This is the Crab Nebula. This is a picture from the Webb telescope of the Crab Nebula, the remnants of a supernova. And if you look right in the center, right about here, there's a bright dot, and that's a neutron star in our own galaxy, the core of the Crab Nebula. So these are the pictures from Hubble. Hubble emphasizes what we see from visible light, and JWST emphasizes what we can get from infrared light. You can correlate the structures between these two things, and again, find some really crunchy science. There's another telescope that's brand new that just went up called the Euclid telescope. It's got a wide field of view. And so one of the things it's supposed to do is do a survey of about a third of the night sky, and it'll allow us to allow astronomers to map the distribution of dark matter in the universe, among other things. So, but it makes gorgeous panoramic pictures. Who can resist? This is the Euclid telescope. Remember, wide-angle view? We talked about the Horsehead last time I was doing Science Sunday. This is a modern view of the Horsehead Nebula. And there it is. You can see why it's called the Horsehead. Although, I don't know, I think it could be called the Zebra Head just as effectively. All right, and then there's OSIRIS-REx, right? Call back to Egyptians. OSIRIS, Origins Spectral Interpretation, Resource Identification, and Security. Regolith Explorer, OSIRIS-REx. Astronomers have a sense of humor. I guess some particle physicists do too. Quarks, up and down quarks. Anyway, this thing went out, touched an asteroid, scooped up a bit of it, came back to Earth, and deposited that stuff into a lab where we can't get to it. So there's a couple of bolts in this container that the scientists can't open, and I'll tell you why in a moment. But fortunately, you see all this black gunk? This is material from the asteroid. So they've got a lot of this material to look at, and they're finding that it's replete with carbon. So that's pretty cool. And here's why they can't open it. It's because it's sealed in an environmentally contained safe room. I don't know, what incubator kind of thing, like you put a baby in, right? And in order to open it, they have to get a tool inside that thing that they can manipulate with their hands to get the thing open. So it's not like we're not, like astronomers don't know how to use a wrench. It's just, it's difficult to actually get the right tool with the right shape that you can apply the right force in this small space. So they're still working on that. Speaking of asteroids, there's an asteroid out there that they think is mostly metal, including gold.
Yay.
There's my cosmic ornament. My final cosmic ornament for today is this asteroid, which may be made primarily of gold. Could be worth, like $6 trillion dollars, or maybe it could be worth $10 trillion, or maybe it could be worth $10,000 trillion at current market prices for gold and iron and platinum and some of the other metals. This could be a $10,000 trillion motherlode of heavy metals that we could use on Earth. Of course, what happens when we get those to Earth? The price of all those metals will plummet because everybody can have gold, which would be awesome because gold's pretty. And
It could be fool's gold.
it could be. Actually, there's a lot of scientists who think that the original density measurement of this was off a bit. So when the probe that's going to examine it gets there in 2029, it was launched just this year. Why it's here today? Why it's on my slide. But when we'll know for sure in 6 years or so, 5 years. But in any case, it's an intriguing idea that we could start mining asteroids for rare materials. And every bit of gold we have on the planet, including the gold in your wedding rings and the gold in any jewelry you have, etc. Every atom of gold we have on our planet comes from the exploded heart of a dead star. Right? So I've got a little gold. I've got on my wedding band, I've got a little meteorite iron, and I've got gold. And the gold isn't there because it's valuable and eternal and all that hokey stuff. It's there because this was once in the heart of a supernova. Every bit of gold was. Beautiful. Talk about a cosmic ornament. And that's it for today. Thank you for showing up.
You're welcome to go and see the service with some beautiful singing in the other part of the building, or Scott, I'm sure, will be ready to answer some questions and talk about anything else with you too. Have a happy holidays. Thank you for coming in. And the next one is going to be at 11:15 next Science Sunday, 11:15, January 7th. All right. It's going to be later in the day. There's only one service on that first Sunday in January.